Okay, in the second part of 1.2, we are looking at transformations. Transformations have been something you've looked at in different math classes over the year, but here today we're going to make sure they're all compiled in one set. So we have first up our reflections, reflection across the x-axis and reflection across the y-axis. When you are talking about reflecting across the x-axis in terms of a function, you would be writing negative f of x. And in terms of a coordinate rule, you would be writing the coordinate point xy goes to x negative y. The reflection across y-axis then would be very similar. F of negative x would be the function notation, and a coordinate point rule would be the coordinate point xy goes to the coordinate negative xy. The memory cue here to help you with remembering which one is which is that if you are reflecting across the x-axis, and so pretend for a second you have a point maybe here at 1, 3. If you reflected across the x-axis, you'd be at 1, negative 3. Your x stays the same, right? It's the kind of, we'll call it the pole around which we are reflecting, right? And so because the x would be staying the same and reflecting across the x-axis, notice in your coordinate point rule that x stays the same. And within your function notation, look at the x in here, the x stays the same. Meanwhile, the y is the thing that's changing. The y changes sign, or out here, f of x, remember, is relatively synonymous with y, and if we multiply a negative to it, the y as a whole is now changing sign. With the y-axis, now the y is going to be staying the same, because the y-axis is the pole across which we are reflecting. And so the y stays the same in your coordinate. The x is what changes now, so y stays the same. And then over here in your function notation, you see again that similarity, right? The x is changing, but the y, my f of x here, is staying the same. And so again, across the x-axis, x will always stay the same, y will always change. Across the y-axis, y will stay the same, x will change. Okay? And then we have translations. So two different ways that translations can be shown. First one is in a rule. So we have translating right or up. You'd be looking at an x plus or a y plus. X plus here indicates a right movement, and y plus indicates an up movement, right? And so for example, if we were looking at this rule, this tells us that we are going right 3 and up 1. Meanwhile, left or down, which are negative directions, would be a negative inside of your rule. So this is your, let me actually bring this a little bit further down there. Okay, this is your left and your down. And so same thing within this rule, x minus 2 would tell us we are moving left 2, and y minus 3 would tell us we are moving down 3. Okay? And that would be the coordinate rule for a translation. Last bit here, so still working with translations, we do have function notation for translations as well, so just like we have function notation up here for reflections. Our function notation for transformations is that if you have your f of x, which remember is somewhat the same thing as y, so this is y plus or minus a number. Well, in the same way that y plus a number meant up or y minus a number meant down, if you see f of x plus or minus a number outside the parentheses, then that translation is up or down dependent on the sign, right? And if you want to, maybe you note plus means up and minus means down. Okay? And then we have our f. Now the x is plus or minus a number. Well, remember x was right or left. But this one here, just for the record, is the trickiest one of the lot in my experience. So I'm going to put careful because what makes this particular function notation here so especially tricky is that it goes opposite of the way you think it would, right? Up here, this makes sense. If I add a number to my x, so say my x was 1 and I add 3 to it, that would be 4. well, that moves me to the right, right? Oops, that wasn't on the screen here. If I was at x equals 1 and I added 3 to it, that would be 4. That would move me to the right. X equals 4 is right, so adding 3 moves me right. Subtracting 3 moves me left. However, in function notation, it's always opposite. And I'll demonstrate why as we get into the example problems, but you want to be careful with function notation because f of x minus a number actually tells me to move right. And f of x plus a number actually tells me to move left. It's opposite of what we think it would be based off of our coordinate rules, right? So all of the other rules, they make sense. It is only this one when there's a number inside the parentheses that you need to put a little check in your brain and go, wait, I have to stop and I have to think about that because that function notation is telling me to move opposite. When, again, only when it's inside the parentheses. Okay? And again, I'll demonstrate why when we get into examples. Okay? Okay, so practicing a few of these, we have 4 examples that we are going to do here. We're going to start by graphing the 2 functions, and then we're going to describe the transformations from the first to the second function. Okay? And so if you need to, go ahead and pull out your function family reviews from last week. Okay, but let's take a look here. Graphing j of x, I'm going to go ahead and turn this into descriptive form by subtracting the 1 over to the other side. So we have minus 1 equals 1/2 to the x minus 3. And so your starting point here, what zeroes out your origin, would be 3, 1. 1, 2, 3, 1. And remember, with an exponential, that starting point is your asymptote. Okay, and then we need 2 other points, and so you can plug in whichever ones you want. Like I said previously, I always like starting with the x I've already found, because when I take that x that I've already found and plug it in here, my exponent is going to be 0, right? And anything to the 0, so 1/2 to the 0 is 1, and then plus 1 is 2. And so my first point is at 3, 2. Okay, and then one more. So when I plug in, you can plug in 2, you can plug in 4. I'm going to go ahead and plug in 2 here. When I plug in 2, I get 1/2 to the 2 minus 3, which is 1/2 to the negative 1. Well, remember, what does a negative exponent do? It flips that fraction, right? So that 1/2 is going to become a 2 plus 1, which is 3. And so that's my second point, is at 2, 3. And if you want to, you could plug a few more in. Maybe you plug in 1. If you plug in 1, you'll get 5. Right? Maybe you plug in 4. If you plug in 4, you'll get 1.5. Right? So you can plug in some more points if you'd like to give a little bit more structure to your exponential, but you do not have to. And then this is j of x that we have just graphed. Okay? Okay, then we are going to graph the other function as well. So this tells us that k of x is equal to j of negative x. And so then the question is, well, what transformation is that? Okay, well, you can look up above if you need to, but again, at some point we need to have this memorized. So when I see multiplying by a negative, that tells me that this is some sort of reflect. The question is, what am I reflecting across? And so then that is dependent upon what is negative. In this case, my x is what is negative, so I'm not reflecting across the x-axis. Remember, if I reflect across the x-axis, my x actually stays the same in both my coordinate rule and my function notation, right? It is when I reflect across the y-axis that x changes sign. The y would stay the same. And so this is reflect across the y-axis. Okay? And so then let's go ahead and do that, reflecting across the y-axis. So this point here is 1 away, so we're going to go 1 away on the other side, right? Here we are 2 away, so 2 away on the other side. 3 away, so 3 away on the other side. And so on and so forth. And you can get your reflected exponential, that is k of x. Okay. And then last bit, so describe the transformation from the first function to the second function. Here in our notes, we are going to do it both ways. We are going to describe in words as well as in rules. Okay, so we've already described it in words, reflect across the y-axis, so what would the rule be? Well, our coordinate rule would be that each of my coordinate points, x, y, would become, and then again one more time, since I'm reflecting across the y-axis, the y is going to stay the same, and the x is going to change because we aren't reflecting across the y-axis, so we aren't oriented around the y, or we are oriented around the y-axis, so the y needs to stay the same. Okay? And then we already have function notation up here, so we don't need to do anything with that. Oh, excuse me. Okay, let's go ahead and do number 3 next. That way, because 1 and 3 are the most similar, that way if you feel like you've got a somewhat of a handle on it and maybe you want to pause the video and try it on your own, go ahead and do so. But we are going to walk through number 3 here. Okay, so we've got a quadratic. Let's go ahead and turn it into its descriptive form. So this is g of x, adding the 3 to the other side. Where's your starting point? Okay, well, 0 would 0 out the x, negative 3 would 0 out the y. Okay, and then we have our a of negative 2, which remember is always over 1. And so this is down to over 1. Or a reminder, if you don't like the a thing, then you could always do an XYT chart, give yourself a couple more points that way. And then make sure this stays a u, don't make it too pointy. It's not an absolute value, it's not a v. Okay? Okay, and then the other one is h of x equals negative g of x. And so what kind of transformation is that? Okay, well again, one more time. Negative tells me, as soon as I see multiplying by a negative, I'm thinking it's a reflect. And so then reflect across what depends on what is negative. What's negative in this case? Okay, well the x isn't negative, right? Which means the y is negative. The x stayed the same. And so since the x didn't change, our x-axis is what we reflected across. The y is what is changing, so we aren't reflecting across the y-axis. So reflecting across the x-axis, we are 3 away, so 3 away in the other direction. 5 away here, so 5 away in the other direction. And you've got your h of x. And last bit describing this. Okay, so we already have our function notation, h of x equals negative g of x. And our coordinate rule would be that each coordinate point x, y would become, and since I'm reflecting across the x-axis, x stays the same, y is what's changing sign. Okay? 2 more in this form here. Number 2, we have our j of x and k of x here. Now notice between j of x and k of x, there's nothing that indicates multiplying by a negative, so we're not doing a reflection here. This is going to be some sort of translation of some sort. So we could even write translate here. Okay, so let's go ahead and graph j of x. So j of x, turning it into its descriptive form, we'd be subtracting 1 to the other side. And so what's your starting point? Okay, well 3 would 0 out my x here, 1 would 0 out my y, and again one more time, remember that for an exponential, you've just found the asymptote. Okay, 2 additional points, XYT chart. Let's go ahead and plug in 3, because that's the x I've already found, and I'm going to plug in 4 as my other point. Okay, when I plug in 3, I get 3 times 2 to the 3 minus 3, which is 2 to the 0, or 1, plus 1. And 3 times 1 is 3, plus 1 is 4. And so that's my first coordinate point at 3, 4. And then I'm going to plug in 4 as well. When I plug in 4, I get 3 times 2 to the 4 minus 3, which is 2 to the first, or just 2, plus 1. 3 times 2 is 6, plus 1 is 7, and so there's my second point at 4, 7. And again, you can plug in other points. If you plug in 2, you will get, let's see, 2.5. So if you plugged in 2, you'd get 2.5. If you plugged in 1, you'd get 1.75, right? So you could plug in additional points if you wanted to help you structure that exponential. And you can do that with all the function families. Okay, and so then k of x is up next. Turning k of x into its descriptive form, we'd be adding 2 to the other side. So what's your starting point? 1 would cancel out the x, negative 2 for the y. And so that's my asymptote. Okay, and then 2 additional points. We have, I'm going to plug in 1, and I'm going to plug in 2 as my other point, although again, you can choose. When I plug in 1, I get 3 times 2 to the 1 minus 1, which is 2 to the 0, or 1 minus 2. 3 times 1 is 3, minus 2 is 1. So 1, 1 for one of my points, 1, 1 right here. And then plugging in 2, I get 3 times 2 to the 2 minus 1, which is 2 to the first, or 2. Minus 2, which is 6 minus 2, or 4. And so 2, 4 is my other. And again, one more time, you can plug in others. If you plug in 0, you'll get negative 1/2, and so on and so forth. Okay, and so that's graphing. Okay, so describing, let's go ahead and finish our description in words. Translating, so we started here at j of x, and then we ended up here at k of x, and so you can use whichever 2 corresponding points you want. If you want my recommendation, I would use the points that created your asymptotes. They're usually the ones that are the clearest to see after you've graphed both functions. Although again, any 2 corresponding points would work. But so if I started here and went to this other asymptote, how did I just move? Well, I moved down 1, 2, 3, and left 2. So translate, down 3 and left 2. Okay, so that's in words. Our coordinate rule, x, y, goes to, okay, well, down 3, is that, first of all, does that affect x or does that affect y? Okay, up and down affect y. And down 3 specifically would be plus or minus. Okay, well, down would be y minus inside of your rule here, right? So this would be y minus, whoops, minus 3. And then what about your left 2? Obviously, we know now it's x. Is that plus or minus inside of your coordinate rule? Okay, well, left is minus inside of our coordinate rule, x minus. Okay? And then for our function notation, this is the one where we want to be careful here, right? Whoops, k of x. Right? How did we get k of x from our j of x? Right? How did we get k of x from our j of x? Well, we went down 3 and left 2. So down 3 is not the one that's usually tricky for people. I'm going to leave a space here. Okay, down 3 is our y, right? So it's our function plus or minus its number. So down would be minus. So it would be down 3. The one that's tricky is the left and right, what goes inside of your function. Right? And so in this case, remember, it's always opposite. So since we want to go left 3, we actually need to do plus, or sorry, left 2, we actually want to do plus 2. And then really quickly, I want to show why that's the case. Like I said earlier, if you already know why, maybe you want to fast forward, go ahead and do so. But for those who have never seen why, here's why. We have just told people in our function notation how we got k of x, right? We take our j of x and we move left 2 and down 3. The reason this has to be opposite is for this reason. Say, for example, well, let's do it at x equals 2 here. Right, at x equals 2. If I'm trying to figure out what happens at x equals 2, right, which for k of x I know when x equals 2 my y was 4. Okay, well then for my j of x I need to move right 2 to figure out what j of x's value is. Right 2 tells me j of x's value was up here at 7. And then with that 7, I'm going to subtract 3 to get my 4 that is in here, which is why the point for x equals 2 on k of x is located at y equals 4. Because we've gone right 2 for our j of x, figured out what that value was, it was 7, and then subtracted 3 from it to actually get our 4 value that we know we're supposed to get from k of x. Okay? So again, careful with what's inside. What's inside in function notation is always going to be opposite. Okay, let's go ahead and do one more. If you feel like you've got somewhat of a handle on it, maybe you pause the video, try as much of it as you think you've got, restart the video either when you're stuck or have an answer, whichever one you prefer. Okay, well, let's take a look here. We have b of x. Let's go ahead and turn it into descriptive form, subtract that 4 to the other side. And what's your starting point? Okay, my starting point is -1 for the x and +4 for the y. And your slope for this linear absolute value is 3, just telling me I'm going up 3 over 1. And I have my b of x. Okay, let's do c of x now. Turn it into descriptive form. I'm going to subtract this 2 to the other side. And what would be your starting point? Okay, well, my starting x would be 0. My starting y would be 2. So 0, 2. And the slope for this linear absolute value? Well, your slope is 3. So let's go up 3 over 1. In both directions. And that's your c of x. Okay. Okay, describing this, well, what just happened? So translate, because that did not flip, that's not a reflection. Starting from b of x going to c of x, b of x went down 2 and right 1. Oops. Down 2 and right 1. Right, to get from my vertex of b of x to my vertex of c of x. Okay, coordinate rule. What does that mean happened? Okay, well, down 2 is that x or y? Down. Okay, that would be y, and then is down plus or minus? Okay, that would be minus. So we have y minus our 2. Right then is x. Is it plus or minus? Okay, right is plus. Plus 1. And then for our function notation, we got c of x by taking our b of x and doing what to it? Okay, well, we got our c of x by taking b of x and moving down 2. So how do I write down in function notation? down would be a minus on the outside of our function. So this is down 2. And then this one's going to go inside, but remember one more time, careful, careful, careful about what's inside, right? It's always opposite. Right, therefore, is going to be minus my 1. Okay? Okay, if there are any questions, write them down now so that when you get into class, you can ask them.